Multimetallic Nanoparticles, Synthesis, Characterization, Properties, and Applications. Multimetallic nanoparticles, MMNPs, including bimetallic, trimetallic, and high-entropy alloy, HEA nanoparticles, have emerged as an important class of nanoscale materials because of their highly tunable structural, electronic, optical, and catalytic properties. By integrating multiple metallic elements into a single nanostructure, MMNPs exhibit synergistic effects that are often unattainable in monometallic systems. Recent developments in colloidal chemistry, seed-mediated growth, and nonequilibrium synthesis strategies have enabled the production of compositionally controlled and structurally uniform MMNPs with enhanced catalytic and physicochemical performance. The growing interest in MMNPs is largely driven by applications in heterogeneous catalysis, electrocatalysis, energy conversion, environmental remediation, sensing, and biomedical technologies. In particular, high-entropy alloy nanoparticles containing 5 or more metallic elements have attracted considerable attention because their configurational complexity generates unique electronic structures, lattice distortions, and surface chemistries that significantly improve catalytic activity and thermal stability. Structural classification of multimetallic nanoparticles. Multimetallic nanoparticles can generally be classified into homogeneous and heterogeneous structures. Homogeneous structures include random solid solution alloys and ordered intermetallic compounds. In solid solution alloys, constituent atoms are randomly distributed throughout the crystal lattice, whereas intermetallic compounds possess chemically ordered atomic arrangements with specific stoichiometries. Ordered intermetallic MMNPs often exhibit superior thermal stability and corrosion resistance because of stronger metal-metal bonding interactions. Heterogeneous MMNPs include core shell nanostructures, heterodimers, and multiphase architectures in which different metals form distinct crystallographic domains separated by interfaces. These interfaces frequently induce electronic coupling, strain effects, and modified adsorption characteristics that enhance catalytic selectivity and reaction kinetics. High-entropy alloy MMNPs represent an advanced subclass containing 5 or more principal elements in near equiatomic proportions. HEA MMNPs possess high configurational entropy that stabilizes single-phase structures and promotes exceptional resistance to phase segregation, sintering, and thermal degradation. Recent developments in synthesis strategies. Seed-mediated colloidal synthesis. One of the most significant recent advances in MMNP synthesis has been the development of seed-mediated colloidal growth methods. Conventional co-reduction strategies often struggle to produce compositionally uniform MEMNPs because metal precursors possess different reduction potentials, decomposition kinetics, and crystal structures. Consequently, uncontrolled nucleation and phase separation commonly occur. Recent studies published in Science demonstrated a highly effective strategy for synthesizing pentametallic MMNPs composed of ruthenium, iron, cobalt, nickel, and copper. In this approach, ruthenium nanoparticle seeds were introduced into precursor solutions containing metal acetylacetonates and heated under controlled conditions. Surprisingly, increasing the number of metal components improved compositional uniformity instead of causing greater phase separation. The resulting RUFECONICUMMNPs exhibited highly uniform particle sizes of approximately 20 to 25 nanometers and consistent elemental distributions. Time-resolved studies revealed that Cu initially deposited onto Ru seeds, followed sequentially by CO, Ni, and Fe incorporation. The cooperative miscibility relationships among the metals promoted heterogeneous nucleation on pre-existing particles while suppressing independent nucleation events. This work demonstrated that carefully designed kinetic pathways can overcome thermodynamic incompatibilities between different metals. The synthesized pentametallic MMNPs exhibited catalytic ammonia decomposition rates nearly 4 times higher than pure Ru nanoparticles at elevated temperatures. A related seed-mediated strategy has also been developed using platinum, palladium, and gold nanoparticle seeds for HEA-MMNP synthesis. In one representative example, platinum seeds were reacted with cobalt, nickel, copper, and zinc precursors in olelamine at 350 degrees Celsius, yielding highly uniform PTCONICUZNMMNPs, approximately 5 to 6 nanometers in diameter. Olelamine simultaneously served as solvent, surfactant, and reducing agent, facilitating controlled heterogeneous nucleation and alloying while suppressing galvanic replacement reactions. Co-reduction methods. Co-reduction remains one of the most widely employed solution phase methods for MMNP synthesis. Multiple metal precursors are simultaneously reduced in the presence of surfactants and stabilizing ligands. Reaction parameters such as precursor concentration, reducing strength, solvent polarity, temperature, and ligand chemistry strongly influence MMNP composition and morphology. A classic example involves the synthesis of FePT-MMNPs through co-reduction of FeCl2 and platinum diacetoacetate PT open parenthesis ACAC close parenthesis. 2. Using lithium triethyl borohydride as a reducing agent in dioctyl ether with oleic acid and olelamine ligands. This approach enabled precise control over particle size and alloy composition. High-temperature and non-equilibrium synthesis. High-temperature methods such as laser ablation, microwave heating, electrical pulse heating, and rapid thermal shock processing have also become increasingly important for HEA-MMNP synthesis. These techniques rapidly heat precursor mixtures to extreme temperatures, followed by ultra-fast cooling, kinetically trapping metastable multi-component solid solutions before phase segregation can occur. Rapid thermal shock synthesis has enabled the preparation of HEA-MMNPs containing combinations such as iron, cobalt, nickel, platinum, ruthenium, FeConIPTRu, and cobalt, chromium, iron, manganese, nickel, COCrFeMNNI, with highly uniform elemental distributions. Such non-equilibrium techniques are especially valuable for synthesizing systems with otherwise immiscible metals. Annealing-induced intermetallic formation. Ordered intermetallic MMNPs are commonly produced through post-synthetic annealing of initially disordered alloy nanoparticles. Annealing at temperatures between 500 and 900 degrees Celsius under reducing atmospheres promotes atomic diffusion and ordering transitions. For example, L10 structured FePT, COPT, and PTNIMMNPs are often synthesized by annealing disordered alloy precursors. Protective coatings such as MgO, SiO2, graphitic carbon, or sulfur-doped carbon are frequently employed to suppress nanoparticle sintering and aggregation during high-temperature treatment. Characterization of multimetallic nanoparticles. Accurate structural and compositional characterization is essential for understanding MMNP performance because catalytic and electronic properties are highly sensitive to atomic arrangement and surface composition. Transmission electron microscopy, TEM, and high-resolution TEM, HRTEM, are routinely used to determine MMNP size, morphology, lattice spacing, and crystallinity. Scanning transmission electron microscopy coupled with energy-dispersive X-ray spectroscopy, STEM-EDS, enables elemental mapping at near-atomic resolution, revealing compositional heterogeneity and interfacial structures. X-ray diffraction, XRD, is employed to identify crystal structures, distinguish solid solution from intermetallic phases, and evaluate lattice strain. Shifts in diffraction peaks often indicate alloy formation and lattice distortion induced by multi-element incorporation. X-ray photoelectron spectroscopy, XPS, provides information regarding oxidation states, surface electronic structure, and charge transfer interactions between constituent metals. Unique physicochemical properties. The remarkable properties of MMNPs arise from synergistic interactions among constituent elements. Electronic interactions between surface and subsurface atoms alter the d-band center of active catalytic sites, thereby modifying the adsorption energies of reaction intermediates. Lattice mismatch between different metals introduces compressive or tensile strain, which further tunes catalytic activity. The local arrangement of atoms on MMNP surfaces generates distinct adsorption geometries and reaction pathways. These ensemble effects can significantly improve selectivity for complex multi-step reactions. HEAMMNPs additionally exhibit configurational entropy stabilization, sluggish atomic diffusion, lattice distortion, and cocktail effects, collectively enhancing thermal stability, corrosion resistance, and catalytic durability. Catalytic applications. Catalysis remains the most important application area for MMNPs. Recent RU-FE-CO-NI-CU pentametallic MMNPs have demonstrated exceptional catalytic activity for the decomposition of ammonia to hydrogen, achieving reaction rates approximately 4 times those of monometallic RU catalysts. Such systems are promising for hydrogen generation and ammonia-based energy storage technologies. MMNPs are also extensively investigated for electrocatalytic reactions, including oxygen reduction, oxygen evolution, hydrogen evolution, carbon dioxide reduction, and methanol oxidation. PT-based HEAMMNPs containing Fe, CO, Ni, Cu, and Zn have demonstrated enhanced oxygen reduction activity and durability relative to commercial PT catalysts because of optimized adsorption energies and improved resistance to catalyst poisoning. Heterostructured gold-copper, AU-Cu, MMNPs exhibit remarkable selectivity for electrochemical CO2 reduction toward multi-carbon products. In these systems, CO generated on gold domains spills over onto copper surfaces, where further reduction produces hydrocarbons and alcohols. Optical, magnetic, and biomedical applications. Beyond catalysis, MMNPs exhibit unique plasmonic, magnetic, and biomedical properties. AU-AG and AU-CUMMNPs display tunable localized surface plasmon resonance behavior useful in sensing, imaging, and photothermal applications. FEPT and COPTMMNPs exhibit high magnetic anisotropy and are being investigated for ultra-high-density data storage and magnetic hyperthermia treatments. Despite substantial progress, several challenges remain in MMNP research. Achieving precise atomic-level control over composition, phase distribution, and surface structure continues to be difficult, particularly for nanoparticles containing multiple immiscible metals. Scale-up synthesis with reproducible quality also remains a significant obstacle for industrial applications. Future research is expected to increasingly integrate machine learning, high-throughput computational screening, and operando characterization methods to accelerate the rational design of MMNPs with optimized properties. Advances in colloidal synthesis, precursor chemistry, and kinetic control are likely to expand further the library of accessible multimetallic nanostructures for sustainable catalysis, energy conversion, and advanced functional materials applications.